Yes. Excellent. All right, but let's see if you can get the next one.
Not quite accurate
On, the answer is there's a version of them. Not necessarily, not exact versions of them, but someone has written a version of each of these languages to run on top of the CLR.
So I can't do any physics work because there's no Fortran.
No, this is not a complete list. There is actually Fortress, I believe. I believe we have a. Yeah, we have. So now, okay, but now let's see who can get this one. So we crossed off those top four. Who knows what the remainder have in common?
Users?
Oh. Unfortunately, PHP has more users than we would like. So no, that is not correct. That is true and correlated with the correct answer, but not the answer. These are all languages that have at least 2 implementations on the CLR. So if it's good, yeah, you're going to do it twice, at least twice. So as you can tell, I'm obsessed with languages on the CLR. I'm Joshua Goodman. I'm the group program manager for the Common Language Runtime team. And I thought I would talk about what we're doing in our newest release that's good for languages and language developers and people like you. Why are there so many of these languages? Over 100, Amanda says. I only found 50 on Wikipedia. But there were like 5 more yesterday. So, and it's because we were designed from the start to support multiple languages, and it's really a great platform for building languages on. And one of the things that's really exciting to me, yeah, wow, questions already.
Great platform. So how about immediate types?
Yeah. Immediate types? Let's hold off on some of the. Let me get a little further. And by the way, let me mention. I'd love to hear all of. Part of the reasons I'm so excited to be here is I want to be hearing questions like that. And so Mike and Jesse, can you raise your hand? So I've also brought a couple people from my team. Ian, can you raise your hand? That's Ian who runs the team. So we would all love to hear questions like that, though not in the middle of my talk.
Bad question.
Okay.
Did you really have to go to Wikipedia to see how many languages are in the CLR?
I'm going to go on now. So, right. So what is this? Why are we such a great platform despite not having immediate types? And we're a runtime, but we're also a full-featured set of libraries. And those libraries work well across multiple languages. And part of what I'm going to be talking about today is what do we do to keep them working well across multiple languages, right? One of the nice things about that is one of your users can learn a new language that's right for his problem, but not have to learn all those new libraries. He can use your new libraries too, but if he wants WPF or whatever you didn't want to implement for your language, he gets that benefit. You can run against that new language against multiple hosts, right? Rich clients, but also SQL CLR. Also for Office plugins, all sorts of different things consume the CLR, so it makes your language useful in lots of different places. And the thing that I think is most interesting is the interoperation between languages, right? Letting you write your code in your language, somebody else write their code in theirs, and share across them. I want to talk a little bit about CLR v4. That's what we're working really, really, really hard on, getting ready to ship beta 1.4 now, and tell you why it's such a big release, right? So our very first release of .NET 1.0 was back in 2002. Then we did .NET 1.1 in 2003. Now here's where things get more interesting. In 2005, we did .NET 2.0. But then our next release was an incremental release. It was purely additive, right? So we built .NET 3.0 on top of .NET 2.0 just by adding stuff on. And what that meant was there was a lot of really interesting things we wanted to do in the runtime, things I'm going to be telling you about in this talk, that we really couldn't because we couldn't do them in an additive way that was sure to preserve backwards compatibility 100%. And again, in 3.5, we added more stuff on. And again, there was stuff we wanted to do that we couldn't be doing in that additive way. So meanwhile, since 2005, right, we've had some people on our team adding stuff. But a lot of the team has been doing things that I'll be talking about today, like fixing up our threading, fixing up our garbage collector, making those better in these not 100% additive ways. And so we've been doing a ton of work since 2005, and that's what I'm going to be talking about today. Thought I'd start with a quick reminder. What is the CLR? We have the base class libraries. Mike down here in front helps run the group that does that. Profiling and debugging tools, JIT and NGen, garbage collector, security model, exception handling, loader and binder. All this stuff up on top, unfortunately, is not us, right? So that's other teams like WPF team and WinForms team. The DLR guys, I build the dynamic language runtime. They build that on top of us, and it's great that they can build such. I wish we've about half the talks today have been about dynamic languages of one sort or another, and I just can't take any credit for those because that's just all on top of us. We don't do very much extra for that kind of thing. F# runtime, again, built on top of us. One of the things that's interesting, usually we kind of bemoan the fact that our architecture lines up with our organization. So you find some library somewhere you don't expect it because some other organization did it. But one of the things that actually works out really well is because these guys are different orgs, we build stuff in a general way that they can all build on top of. And we expose those things in a general way that they can build on top of, but that any of you can build on top of as well. And so one of the things you see is that our organizational structure of building a great platform at the bottom and letting lots of people build on top, that actually works out really well for a language developer. Okay, so here are some of the things that we've done in .NET 4 that I want to talk about today, and I'm not going to get through them all. So I'll probably just ask for a little feedback from you guys about what interests you most. I'm definitely going to do at least the first part on types because, we got to do that at Ling.net. And I'll probably tell you about the native code wrapper. I'm leaning against talking about the type equivalence across add-ins because it's a little bit complicated and a little more technical than I've seen in the other talks, but it's kind of cool. Who wants to hear about type equivalence across add-ins? Oh, all right, that's pretty good actually. And we've got Jesse here who's the expert, so I will try to get to that one. Who cares about threading in parallel? Pretty good. Garbage collection? Not so much. The garbage collection stuff is cool. Corrupted state exceptions? And in-proc side-by-side, which is our let two CLRs run the same process. Okay. Good. That gives me some idea of what I got to talk about. So types. We did 3 new types, as well as this type equivalence, which I will do, and this native code wrapper. And maybe I will do that. Maybe I'll skip that one. So here, complex. We're going to have it. Okay. Big integer we will have as well. That one actually turns out to be more interesting. We had an implementation of that in 3.5, and it was too slow. It turns out it's easy to do big integer. It's even easier to do it badly. And so we decided to hold off until we could do it right. And we got help in 4.0 from the Optima Solver Foundation team, which are numerical experts, who helped us do what I thought until last night was a really fast implementation. And then I was drinking with Jeffrey at Rock Bottom, and on my second martini, he says, "So how fast is it?" And he's like, "It's not as fast as mine." And he started explaining to me the algorithm to do it in n to the 1.6 instead of n squared time. And after my second martini, I didn't understand, but it's good, but it's not as good as Jeffrey's.
Really good.
Tuples are probably the most interesting new type we added. And I want to talk about, it turns out, a lot of these things sound simple. And yet, actually, there's a bunch of underlying complexity. And I want to talk a little bit about where that underlying complexity comes from. Right, so why do we want tuples? Well, F# likes tuple, Python's likes tuples. They're actually pretty cool, but there's some hard parts. Yes?
I thought there were tuples in C# as well.
There will be. You're giving away my punchline. Thank you. Yeah. So actually, so one of the things we wanted was when we create these new types, we want to create them in the base class libraries so they can work across all the different languages, right? So that you don't write an F# library that returns a tuple, and then your C# code can't call that library. That would be bad. Yeah. So that's why it's in the BCL. But it's not just enough to have it in the BCL. We have to also make Anders happy. But we also have to make Don Syme happy, and we also have to make Jim happy, right? Because Python needs it too. So we have to make everybody happy. And that's where things get interesting. Right, so give a simple example, right? Should it have referential or structural equality? And C#, most of our compound types use referential equality, like the array class. F# is usually structural, right? And then you get interesting questions like, well, what about nan, right? Because nan equal nan, that's false in any language that knows anything about the IEEE, including F# and C#. But nan dot equals nan is true. And so what about a tuple of nan? What should that be, right? And the answer is it would be pretty weird if this was false and this was true, right? So you really want this to be false. But if you do structural equality naively by recursing with dot equals, you're going to get the wrong answer. And so what we did is we gave the languages control. So a language like C# does nothing, and it gets the default object equal operator, which does the referential equality, which is what it wanted. And a language like F# uses the compiler to map equals to a special method. So we expose this method in the base class libraries that takes an iEquality comparer overload. And then they can pass in an overload that checks whether the thing is a double, does the right thing for nans, and calls equals for everything else, and get exactly the behavior they want. And I just thought this was interesting as an example of how we work, right? We talk to all the different language teams at Microsoft and try to find something that's going to work for all of them. And we try to do it in a general way like this one, so that if a new language comes along that wants to do something slightly different, they have that flexibility. And I think it's part of what makes the BCL so great for language developers. And then your question about do we have it in C#? Yes, we do. And it actually comes out pretty nice. That was another one of the challenges, actually, was, with no compiler support for this, how do we make this moderately pleasant to use? And we've made it fairly easy to declare a tuple. Use generics to make it easy to create a new one on the fly and just figure out what the type is from the types of the inputs. Here with type inference, it's actually quite easy, and there were questions yesterday about doing multiple returns, and we've now made multiple returns really fairly pleasant. And they're not too hard to use either, even without pattern matching in the compiler. One thing that was interesting for me was I gave this talk is a variation on a talk I gave at PDC. I hope none of you have seen it before, even though I know a couple of you have. But I got a fair amount of applause when I showed this. And I was sort of surprised. I had sort of thought of tuples as an F#, Iron Python kind of audience. And the C# developers, which was mostly that audience, they really, really liked this. They wanted this. And it was one of these great moments where we go and we put something into the libraries for what we think is a small audience, but we do it in this general way, and it helps everyone.
Question?
Yeah?
Does that dot item one really lowercase?
I do not remember. It is quite possible that there are typos in this. It is immutable, and that was actually another interesting question, right? Because F# really, really wanted this immutable. C# would have preferred it to be mutable, right? Because arrays are and other kinds of similar and structs are mutable. And we had to go back and forth. But what we decided is, hey, F# is the primary customer for this. If we don't make them happy, we're not really doing this right. Iron Python also wanted it immutable.
I see they can have a very good that's in the tuple generic list.
Yeah, it's up to 7, and then there's a way to do. There's overloads for 7, and then beyond that, there's a general way to do as many as you want.
Okay, so if they're immutable, why don't they work with variants?
I actually had a slide on that. So variants only work with delegates and generics. I'm sorry, interfaces and generics. Is that right? And so delegates and interfaces. Sorry, delegates and interfaces. And so we had an alternate design based on interfaces, where you could create a tuple, but you could also have your functions take an interface as their input. And when we went through that alternate design, what we saw was, it was kind of confusing, because sometimes you had a tuple as an object and sometimes a tuple as an interface. And also, going back to the question about mutability, someone could have created an implementation of tuples that was mutable and passed it to a function that expected something immutable. And so we didn't like the fact that people could be breaking each other in kind of hard to understand ways. So we decided, after talking to the different teams, that keeping it simple was more important than the covariance. Yeah?
That suggests that it might be a really good idea to add variants for classes.
That's an interesting question. I believe that is a difficult thing to do, is my understanding. But we're going beyond my depth of knowledge.
Can I access the members through index?
I don't believe there's an overload for that, and I actually. Yeah, I don't believe there's and I actually have a mail that I didn't finish sending where giving feedback to the team that I thought that was something they should think about. It's particular. Who wants that?
Woo!
Oh my gosh, everyone. Okay, who doesn't want it? Are there certain people who just don't care?
Just raise your hand.
So Josh, you should point out before you have people vote that if you access via index, you only get back object.
Yes.
So if you want access via index that gives you object, I think you're going to get a lot.
Who wants access via? So who wants access via index that gives you object? Okay. All right. I'm going to skip this one, even though it's cool. You missed it. But I'm going to skip. Well, I'll get back. I'll just keep going in order. I want to talk a little bit about what we had to do for F#. Not much. We had to do tuples, and we had to fix a tail recursion issue. There was a tail recursion problem that I didn't actually understand until last night at Rock Bomb again after the 2 martinis, and someone from the F# team, Luke, was explaining to me in detail exactly what he needed and why. But fortunately, we had given him most of it. It turned out that for partial trust code cross assemblies, for mutual tail recursion wasn't supported on 64-bit, and this actually was a good-sized problem for them. So we fixed it. We did that, The good news about being a PM is the way we fix things. I'm a program manager, not a developer, right? So the way we fix things is we send email, and we can do that whenever. So that and tuples was actually all F# needed, and that was actually very cool, right? That a new language class, functional languages, really didn't require very much work to support. Oops. You guys, I'm going to go super quick over the garbage collection thing, even if you don't care. It's pretty cool. The short version is that garbage collection is complicated, and we have all these different pieces, and the big one takes a heck of a long time to collect. And usually we can collect the little one, the ephemeral segment where Gen 0 and Gen 1 are, in parallel with the big one. But if we we can't do that. We can keep allocating on this while we're collecting that. That's our background GC. But if this thing runs out of space while we're collecting that, we can't garbage collect this one on the fly. And so at that point, your program pauses until this big thing is finished. Right? So despite being able to do a bunch of stuff in the background, it wasn't all that uncommon to run into situations where you'd have to wait for the large segment, the Gen 2 collection, to finish. And what we added in CLR v4, oops, there's the punchline. What we added in CLR v4 is our background collection, where we can do a GC on the ephemeral segment even while we're doing a GC up here. And now you get to see the punchline, which is Here's what the old performance looks like. These are pauses. They're bad. These are small pauses. There aren't very many of them, and they're smaller. And so what you see is noticeably less latency in our client garbage collection now. X-axis is just time, so this is just a sample run. And this is. I hope it's microseconds. It is. Look, there we go. Okay, parallel. So, right, we're at the bottom. We don't actually do any of the really cool stuff that makes the really cool demos, right? So you guys have all seen things like parallel.4 and parallel.4 each. Who's seen this? Okay, good. Yeah, and we didn't do it. But we built the stuff that's built on, right? In particular, all that stuff is built on top of our thread pool. And in fact, anybody can build on top of our thread pool. You can go creating threads however you want. Now, our thread pool is actually a fairly clever one, right? We let you create virtual threads, and then we'll assign physical threads to them as cores free up. And one of the interesting things is how many physical threads should you have, right? So if you have an application that's CPU bound, you probably want about as many physical threads as you have cores. But if you have an application that's, say, doing some disk and doing some network and doing some talking to a database somewhere, and so there's a lot of latency where it's waiting for those things to come back, then you want to have a lot more physical threads than you have cores, because a lot of those threads will be blocked a lot of the time. But you also, it's not just about the CPU, right? You could thrash your disk or other things. You create too many physical threads, you'll thrash one of those other resources. So it can be very, very difficult just by looking at resource usage, right? Something that could be a SQL Server box somewhere far away that you have no access to. It can be really hard to figure out what's the right number of threads to optimize your throughput. So one of the things we're shipping now is a new, what we call a hill climbing algorithm that will actually dynamically over time try adding one, subtracting one, changing the number of physical threads, and watching how does that impact the overall throughput of the system. And do statistical analyses, make sure it's got enough data to be statistically significant, make sure that the times it's looking at are long enough, because you might have very short threads, very long threads, and it's much better than our older algorithms at matching whatever weird situation it gets put into. Additionally, the new algorithms are lock-free, so they scale better. Right, so what does this mean for you? Well, if you're using something like parallel.4, it works better. If you're building your own parallel libraries, whatever parallel thing you want to be building on top of a runtime, we've given you a better building block to build on top of. How am I doing on time?
Come on, go.
5 minutes. All right. I'll skip this one. And I'll skip this one. And I'll get to this one, type equivalence. This is a kind of cool one, right? Because what I liked about this one, why I thought this would interest this audience, is we're used to thinking about type equivalence in terms of libraries talking to each other, or covariance and contravariance, and a lot of that kind of thinking that's very programming language centric. And we came up with a very interesting, very applied problem that was causing real pain for end developers. That was a kind of different take on type equivalence, and I thought it might interest you to see that other direction of thinking about this. So imagine you have an add-on that needs to run against Microsoft Office, which a lot of our developers do. That's one of the great places to use .NET. Office has thousands and thousands of APIs for these add-ins exposed through COM, but COM was designed for native code. So we have something called interop assemblies, or IAs, and those help us translate between managed code and COM. They contain the marshalling information that we need to translate from managed to native. And so for each interface struct enum or delegate, there's a managed equivalent with that marshalling data. Now it turns out, and this is where things get more interesting, it turns out that the add-ins often need to talk to each other, right? So a good example of that is if you have a cell in Excel that's calculated through one of these add-ins, and it has a result that's depended on by another one of these add-ins, it turns out that those guys need to be able to talk to each other because of the way the Excel add-in model works. And if they're going to talk to each other, that means that the types they use for talking have to be the same. And the rules we've used mean that means that those types have to come out of the same assembly. So we have something called a PIA, a primary interop assembly, and people have to deploy that PIA with their app. And it turns out these PIAs are a pain in the neck. It turns out getting them onto people's machines is a pain. So the Office one is, I can't remember, it's 10 or 20 megabytes. It's huge because they have such a large programmability model. And meanwhile, often people deploy Office without deploying .NET. So Office can't deploy the PIA because it has to go into GAC so that everybody gets the same one. And the GAC might not be there if .NET isn't there when Office is installed. So that means the application has to pull this PIA along with it. Each add-in has to bring along the PIA. So you might have a 100K add-in bringing along a 20 megabyte PIA, which kind of upsets people. So what we've done in CLR4 with help from the compiler teams is we've made it so that the compiler can embed the portion of the interop assemblies that the add-ins actually use down to the method level. So they put in just the types that guy uses. And the runtime is going to make sure that these definitions are considered equivalent. This is even though they're in different assemblies, and even though they might have different subsets of those interfaces, right? So it's like the opposite of duck typing. We don't care if you go quack and you go ack. If you both say you're a duck, you don't have to sound like a duck, you don't have to look like a duck, you just have to say you're a duck. If you both say you're a duck, which in this case is your comgwid, so if you use the same comgwid, we're going to believe you're a duck. So what if you want to implement this in your own compiler? Because this does require compiler support, and that's something that's coming soon. We're putting together Jesse here. Raise your hand, Jesse. Jesse is working on the explanation of exactly what you'd need to do. So to sort of sum all this up, the .NET framework was designed from the start for multiple languages. I thought we were up to 50, but it sounds like we're up to over 100. Our platform model, right, we're building a core runtime, and then all those other teams get to build on top of us. That really works great, both for us, but also for you. We have things like framework design guidelines that keep it all consistent. We have security reviews, we have compatibility reviews. So as we're doing all these things, we keep building this great set of libraries for you to use. This was the half-hour version of the talk focused on Lang.net. There's a whole lot more in there, right? This was lots and lots of people working for 4 years, so there's more than I can talk about in half an hour. There's a PDC version of this talk that you can find easily with your favorite search engine, whatever it may be. And we also have a new CLR team blog where we're aggregating all the information we're putting out. And as we get close to beta 1, we're putting out more and more information there about what's in the new release. Thank you very much. I'd love your feedback of whatever sort, because we're also starting to think about our next release, and we want to know what else we should be doing. Thanks very much.